In this video, we're going to talk about 3 different ways to define a projection, the last of which will be defining a projection as a linear transformation. But before we get there, we want to just remember what we're talking about when we talk about a projection. So let's say, for instance, that we have just our 2 coordinate space here, and we'll just mark off 1, 2, 3, and 1, 2, and then 1, 2, 3, and maybe 1, 2. So we have the x-axis and we have the y-axis. And let's say we have a line that looks like this. So we'll sketch this out in 2D. And we'll say that this line here passes through the point 2, 1. Let's call this line L. And we can say then that L could just be defined as all the scalar multiples of this vector 2, 1. Because if we think about the vector 2, 1 as the vector from the origin here out to this point that's on L, if we just scale that vector by positive multiples or negative multiples, we'll get all of the points along this line. And so with the vector 2, 1, we can create the line L. In the same way, if we had the vector 4, 2, or the vector -2, -1, all of those lie along the same line as well, so we could equally use those to define the line, but we'll just use 2, 1 because it's a nice positive, simple way to think about L. So we could almost say that L is all the scalar multiples of the vector 2, 1. Now, if we want to define some vector, we'll call it V, and let's say the vector is 1, 2. So it's sitting above L like this. And we want to talk about the projection of this vector onto L. Well, the way you want to think about this is that you almost have some sun source up here. So you have a sun, it's shining its light from up here down onto these 2 vectors. We'll call this the vector V. You want to think about the shadow that V makes on L. And that shadow is always just going to be the line that's perpendicular to L that connects L to the tip of V. So maybe it looks something like this, but the point is that this is a 90-degree angle right here. The projection of V onto L then is specifically this vector right here. It's the shadow of V on L. So if we make this shadow of V on L, that is the projection of V onto L. And we write that this way, the projection of the vector V, so we say the vector V, onto the line L. Now, of course, we've already defined a vector that lies along L. It was this vector here, 2, 1. Let's say we call this vector the vector X, and so that's this vector right here. Well, notice that the projection vector here and the vector X are collinear. They are parallel, so they're scaled versions of each other. So we can actually say that the projection of the vector V onto L is some scaled version of the vector X, where the vector X is the one that we use to define the line in the first place. Now, as it turns out, if we do some manipulation here, we can actually prove that this value C is equal to the dot product of the vector V, the one that we are projecting here, and the vector X, the one that we use to define the line L, divided by X dotted with itself. So X dot X, which means that if we want to find this projection vector here, the projection of V onto L, instead of writing that as C times the vector X, we could actually write that as this quantity here, the vector V dotted with the vector X divided by X dotted with itself, and then that whole thing multiplied by the vector X here. So in this example, we already know that X is 2, 1. We're saying that V is 1, 2. So V, we said, was 1, 2. So we can actually calculate this projection vector here, the purple one. We can say that this is equal to, so let's go ahead and find these. We have the vector V, which is the vector 1, 2. So we'll dot 1, 2 with the vector X, which is 2, 1. And then we'll divide that by X dotted with itself. So 2, 1 dotted with itself, 2, 1. And then we'll multiply that by X, 2, 1. So the result here then, if we find this dot product, 1 times 2 is 2. 2 times 1 is 2. So 2 plus 2 is going to give me 4. And then in the denominator here, 2 and 2 is 4, 1 and 1 is 1, 2 plus 1 is 5. So we get 4/5, and we multiply that by the vector 2, 1. So in this case, 4/5 acts like a scalar on the vector 2, 1. So the result then is the vector 8/5, when we multiply 4/5 by 2, and 4/5. So that vector is the projection vector. We could go ahead and say that this vector is 8/5, 4/5. And we can see that that looks about right because 8/5 is about 1.5, and we can see that this comes out to about 1.5. And 4/5 is a little less than 1, and we can see that this comes up to a little less than 1 along the y-axis. So that looks like it's about right. And that's one way that we can find this projection vector. The other way is to take the vector x that we used to define the line L and normalize it. In other words, change it so that it points in the same direction, but its length is 1. So to do that, if we look at its current length, we can find its current length. We'll say the length of x is equal to, it'll be the square root of 2 squared plus 1 squared. And that'll, of course, be the square root of 4 plus 1, or the square root of 5. So the length of x currently, the vector 2, 1, is root 5. Remember that if we want to normalize the vector x, all we do is take 1 over this length and multiply that scalar by the vector 2, 1. So we'll say that the normalized vector, we'll call it u hat, will be 1 over root 5 multiplied by the original vector here, 2, 1. So when we distribute the 1 over root 5 scalar across the vector, what we'll get is 2 over root 5 and 1 over root 5. So this, the vector u, is the vector that points in the exact same direction as x, which means it lies along this blue line. It's collinear with x, and it's collinear with the projection, but it has a length of exactly 1. The reason that normalizing this vector is helpful, because remember, if we go back to this value c that we used before to find the projection vector, notice here in the denominator we have x dotted with itself. Well, we know that x dotted with itself is the same as the length of x squared. So we could actually call c the vector v dotted with the vector x divided by the length of the vector x squared. Well, if we normalize the vector x and we use u instead, the length of that vector is now going to be 1. And so in the denominator, we're just going to end up with 1 squared, and that whole thing simplifies. So c just becomes the numerator alone, the vector v dotted with the vector x, because in the denominator we ended up with 1 squared, and that simplifies to 1, and dividing by 1 doesn't change anything, which means this projection formula then just becomes the vector v dotted with the vector x, this value down here that we found that remained for c, and then that multiplied by the vector x. But of course here, we've replaced x with its normalized version u, so we can actually call this the vector v dotted with u and then multiplied by u. So we've got this big messy formula all the way down to this simpler formula. And if we use this second method, so we used the first method here where it was this more complicated projection formula, now we're doing the second method where we have this simplified projection formula because of the fact that we normalized x. If we calculate the projection vector this way, then what we get here is the vector v, which we know is the vector 1, 2, so 1, 2, multiplied by the unit vector, which is 2 root 5, 1 root 5, and then multiplied by the vector u, so 2 root 5, 1 root 5. And if we simplify this way, we'll first take this dot product here, so we'll get 1 times 2 root 5 is 2 over root 5, plus 2 times 1 over root 5, or 2 over root 5, so plus 2 over root 5. And that sum is going to be multiplied by this vector here. So then when we add 2 over root 5 to 2 over root 5, we're going to get 4 over root 5. So really we're just left with the scalar 4 over root 5 times this vector up here. So if we multiply this scalar across the vector, the result then is going to be 4 times 2 is 8 in the numerator, and then root 5 times root 5 is 5 in the denominator, and then 4 over root 5 times 1 over root 5 is going to give us a 4 over 5. And notice how we ended up here with the same value for the projection vector. Now our last method, so our first method was using this sort of messy formula. Our second method was normalizing the vector x and then using this simplified formula. And then our third method here is going to be expressing the projection as a linear transformation. So first of all, we want to say that in order for the projection to be expressed as a linear transformation, that projection has to be closed under addition and closed under scalar multiplication. And it turns out that those two things are always true. So the rules here are that the projection of the sum of two vectors, which itself is a vector, so let's say the sum of vectors A and B, the projection of that vector onto L is going to be equal to the projection of the individual vectors onto L. So the projection of the vector A onto L plus the projection of the vector B onto L. That's the property that tells us that we're closed under addition. And then to be closed under scalar multiplication, we're saying that the projection of some vector where we scale the vector A by some scalar, the projection of that vector onto L is going to be the same thing as pulling that scalar out in front and saying the scalar times the projection onto L of the original vector A. This property is also true. This is the one that shows us that it's closed under scalar multiplication. And so because we're closed under addition and closed under scalar multiplication, we can say that this is a linear transformation. And because the projection is a linear transformation, that of course means that we can always express it as a matrix vector product. So we can say that the projection of some vector V onto the line L can always be written as the matrix vector product A times V, where A is the matrix and V is the vector. As it turns out, if we normalize the vector x, and so we use this u hat here for the normalized version of x, then we can write A as simply, we'll say u1 squared, and then u1 u2, and then u1 u2, and u2 squared, where the components u1 and u2 come from the normalized version of the vector. So this 2 over root 5 here is u1, and 1 over root 5 is u2. So we definitely want to find A, and we'll use the components of u to do it, and we'll say that A is going to be equal to, if we square u1, well that's 2 over root 5, I square that whole fraction, I'm going to get 4 over 5. So I'll get 4 over 5 here. And then here I want to multiply the two components together, u1 times u2. Well, when I multiply these, I'll multiply across the numerators and across the denominators. So I'll get 2 times 1 is 2, and root 5 times root 5 is 5. I end up with 2 over 5. So I'll get 2 fifths here and 2 fifths here. And then when I square u2, I'll get 1 over 5. So I'll get 1/5 there. And now we have a transformation matrix. And the reason that this matrix is so valuable and the reason why this third method is the best method to use is because this matrix now will not only transform the vector 1, 2 for us, it'll transform any vector that we want to project onto the line L. So if I come up here with a bunch of vectors, let's say I have this vector, maybe it's 1, 1, or I have this vector, -1, -2, or I have this vector here, which is 3, 1. I can take any vector that I want to, and all I have to do to find its projection onto the line L is to multiply matrix A by that vector. So finding matrix A is by far the most versatile use of our time. And so if we want to prove that this works, we can multiply this by the vector V, 1, 2. So 1, 2. And the result here, we'll get 4/5 times 1 is 4/5, 2/5 times 2 is 4/5, so we'll get 4/5 plus 4/5. And then 2/5 times 1 is 2/5, and 1/5 times 2 is 2/5. And so the result here will be 8/5 and 4/5. And we can see that in all three cases, so down here, the value we just found, the value we found just when we normalized the vector x, and the value we found originally when we used the more complicated formula, we got the same result every time. The difference is that in this third method, we were able to find this transformation matrix A that'll allow us to find the projection vector for any vector v that we choose to project onto L.